Hi there, this is the first of two films that you might watch as an introduction to the solutions topic in year 12. These two films kind of go ahead of the five film series about solutions. Okay, and the purpose of these two films is just to remind us of some of the work that we did in the bonding topic about solutions, and also to cover something called ion dipole forces. But in this particular film, we're going to try and remember how it is that we explain the solubility of substances, of certain solutes in different solvents, and we're going to try and just remind ourselves quickly of the definitions of solubility that we find on the data sheet. Okay, so first of all, what happens when things dissolve? Remember, what we're going to try and do every time we try and explain this, why does this substance dissolve in another, we're going to try and identify the forces broken and the forces made, and we're going to make some comparison between those forces. Okay, so before something dissolves, here we've got some barium chloride, which is in a solid state in a beaker of water, presumably. Okay, there are solvent-solvent forces, so that is forces between the solvent molecules that are going to have to be broken to get the solute particles in between them. And there's also solute-solute forces, which are going to have to be broken by the solvent in order to split this solute up. Okay, so by the time we've formed our solution, we've got solvent-solute forces, that is forces between the solvent and the solute. So we're replacing these forces with these ones. Okay, but it's not good enough just to talk about them in these vague terms. You need to try and make sure you're actually identifying what type of solvent-solvent, solute-solute, or solvent-solute forces are actually breaking. Okay, so here's a particular example of one of those type of explanations. Why does petrol not mix well with water? Okay, so let's treat petrol as our solute, although water could equally well be our solute, depending on which one's in the majority. But let's treat this as our solute. Okay, what solute forces have we got? Well, this is a non-polar molecule. Okay, so there's only going to be dispersion forces here. Okay, it's a hydrocarbon. All hydrocarbons are non-polar. Here's water, which is polar, okay, and actually has dipole-dipole forces, but it also has hydrogen bonds, okay. So we only say hydrogen bonds, we don't mention the dipole-dipole forces as well if there's both, because remember, hydrogen bonds are a form of dipole-dipole force, but we do mention the dispersion forces because they're a different type of force. Okay, so we're going to try and be systematic in our explanation. That is to say, we're going to say what forces break and what forces are made, and then make some comparison. So name and compare the forces broken with those that are made. Okay, so we are breaking dispersion forces in the petrol and hydrogen bonds in the water, as well as dispersion. Okay, so this is petrol here, and this is the water, and we're making, well, what forces can we make? Well, only dispersion forces between the petrol and the water. So once we've identified those things, we can say that the dispersion forces that we make are not strong enough, because this thing does not mix well. Okay, so these dispersion forces that we make are not strong enough to overcome the hydrogen bonds and dispersion forces that we had to break between the water molecules. Okay, it's not often the case that you'll have to predict on this sort of basis whether things are going to dissolve or not, because it can sometimes be difficult to know whether the dispersion forces are going to make up for this kind of thing. But if you know that something doesn't dissolve well, then you can say that the forces that you've made are not strong enough to make up for the ones that you broke. Okay, so once again, be systematic. Mention the forces that were broken, mention the forces that were made, and make a comparison between the two. Okay, but actually name those forces. Now just finally, just to look at these definitions of what solubility is. If everything dissolves, then surely everything is soluble. Okay, but that's not really the case, because we define different degrees of solubility in different ways. So we define anything that dissolves more than 0.1 of a mole in every litre of solvent as a soluble substance, anything in this range here between 0.01 and 0.1 is slightly soluble, and we term things that dissolve less than 0.01 of a mole in every litre, we term those insoluble, even though a very small amount of them will dissolve. So for example, if you're looking at oxygen, which is often described as being very, very sparingly soluble in water, or in other words, insoluble in water, that suggests that nothing ought to be able to breathe underwater, but obviously fish do. And if you're going for your forces explanation, then you're going to say, well, the dispersion forces that form between oxygen and water molecules, okay, they're not going to be strong enough to make up for the fact that we broke hydrogen bonds between the water molecules, okay. But clearly, that doesn't mean that none of the substance dissolves, okay. So as far as your forces explanations go, they're just going to explain whether something dissolves well or not. Okay, it's not going to allow you to decide whether something dissolves or not, because really everything dissolves to some extent. So I suppose that's a little bit of a confusing note to finish on, but that's about it for this film. Next film to watch is the one about ion dipole forces.